important because it's very similar or kind of the same type of question as one of your assignments, called solving ILP. So I do want to get the answer right, or the solution method at least. The algorithm was part of the handout. It's described like that. I think we've gone through it. So what you get as your initialization, you're starting with a list of problems to solve. You have the best solution found so far, which is this one, and its objective is the bound. So you have no integer solution to start with, so it's kind of void or nothing. And you have no bound because you have no solution yet. And the first problem is this problem S. So this is what I call S. And we're trying to solve that by branching and trying different options for the decision variables or adding constraints. Okay, so when you're drawing the tree, you can, I don't know, do it in different ways, but I usually do it like this. So I've got this problem S here. And your list will just contain S, and your incumbent bound, there is nothing. So the bound is minus infinity. That's how the whole thing starts. So what you do is you go on your list, okay, and pick something on that list. Well, there's only one thing on that list, so you need to take S, and you solve the LP relaxation of S. And so the LP relaxation is you ignore this integer constraint and just solve it as a linear program. So greater than or equal to 0, yes, but it can be any real values. Or you can do it using this code or something similar, whichever you prefer. There are different ways of doing it. This seems the easiest to me because you just type it very quickly. You can kind of ignore these things. They just tell you whether the problem is infeasible or feasible. But if you check the status in whatever in Express IVE, then you see whether then it's telling you whether it's optimal or infeasible. But the problem is when you just print the solution, sometimes it prints values even though the problem is infeasible because it came up with some values. They don't satisfy the constraints, but that's the last thing it had when it was solving the dual simplex or something like that. And it just, for the first stage, or I don't know what exactly it does, one of those things, and it has some values for the decision variables, but it knows it's not feasible, but it will still print those values if you ask it. So you have to be careful there. However, in this case, the LP relaxation, so when you just solve this problem with linear constraints, what it's going to give you is the code will print Z equals 13.2762, something like that, and X1 will be 2.276, something like that. X2 is 2.905, and X3 is 0.971 approximately. So that's the solution to this problem if you didn't want all the x's to be integer. And I just put it here like this. I know that the 13.2, and then X1 is 2.27 something, X2 is 2.9, X3 is 0.97. Now, because we don't have an integer problem, integer solution, and we don't have any other good reason to stop branching, we add 2 branches. So we create 2 new subproblems. how do we do that? We call them S1 and S2.
You add another condition for x1 because it's the one that's closest to the middle, like 2.5. So you do one branch is x1 is less than 2, and another branch is x1 is more than 3.
Okay, so what you do is you pick one of the variables, x1, x2, or x3, which comes with a fractional value in the optimal solution of the relaxation. Typically, you would pick, as George has said, the one that's the most in the middle between the two integers. So this one is quite close to 3, and this one is quite close to 1. So this one is the farthest away from an integer value. And then because it's something between 2 and 3, and you know you cannot, in the optimal solution, it can never be between 2 and 3, you add, on the one hand, the constraint that is no more than 2, on the other hand, that it's at least 3, and that creates 2 new subproblems, S1 and S2. Okay, so you add them on your list. And you keep repeating this in a loop as long as there are any unsolved problems on your list. Okay, so the next one, it's always a question, which one do I pick from the list? Well, you don't really know because you haven't solved them yet. Or you don't really know because they're kind of equivalent. So if I'm feeling lucky, I'm going to pick S2. And when I'm solving S2, that means that I'm keeping all the original constraints I had, while I'm adding x1 greater than or equal to 3. Okay, so what I would do is here in the code, I just add x1 is greater than or equal to 3. And I run this code again, and it's going to give me a new optimal solution. And in this case, the optimal solution, there isn't, because this problem is then infeasible. So this turns out to be infeasible. And when you have a branch which is infeasible, then you prune the branch. That's the terminology. So you note that this subproblem is pruned by being infeasible. We still haven't got an incumbent because we still haven't found an integer solution. And we don't branch here, so we don't add anything new to the list. Okay? So that was the next step. And now it keeps repeating. So you go on your list, find something that's not been solved yet. Okay, take it off the list. Now, I would change this to less than or equal to 2, like this. Run the solver again. What do I get? I get the objective value is going to be 13, and x1 is 2, x2 is 3.25, x3 is 0.83 in this example. Okay? This is not integer, so we create 2 new subproblems. Call them what you want, S3 or S11. That's up to your taste. And S4. I'm adding S3 and S4 on the list. And which variable do I pick? So maybe I pick x2. You could try with x3 as well and see whether that is any slower or any faster than taking x2. Sometimes you get a lot of branching, sometimes you get lucky and you don't get so much, depending on your choices. But nothing can be guaranteed in advance. So now I go, I'll pick S3, I solve S3. S3 gives me Z is equal to 13, and I get 2, 3, and 1. So that's an integer solution. So that replaces the incumbent. So the incumbent is S3 with x1 equal to 2, x2 equal to 3, and x3 equal to 1, and the bound is 13. So I know I'm trying to maximize. I know that my optimal solution is not going to be less than 13. And I kind of also know that it's not going to be more than 13 when I look at it, but not immediately. Okay, so this is pruned because it's integer. But normally I would continue. I go to S4, and when I solve S4, I get something that's 12.4, and this is 1.44 and 0.53 something. So that's not integer. So I want to branch. Yes? No? No? Why not?
It's not going to be better than 13, so I'm going to get less.
Well, because of the nature of these relaxations, no matter what solution, integer solution I would find in this branch, in this subtree, its optimal objective would never be better than 12.4. So there's no point. We know the optimal solution is not going to be in this subtree, so this one will be pruned because it's suboptimal. And now the algorithm tells me to go on the list and find a problem on the list, but there's no more problems on the list. So what we found as the incumbent, that now becomes the optimal solution. Okay, so the optimal solution we found is x1 is equal to 2, x2 is equal to 3, x3 is equal to 1, and the objective is 13. Any questions about how this goes? Hopefully that is clear. Now, if in the first branching, we said that we're branching on x1, but it's not a big deal if you choose something else. It's just maybe you'll spend more time doing the algorithm. But in this case, I have an example. I'm missing. If you decided to branch on x2, then one of these branches would give you an integer solution, so that's kind of good. And the other one gives you the optimal solution after another branching, and the last one would be suboptimal. So that's an alternative tree. Both give you the same optimal solution. End of. Sorry. All good? So hopefully everybody can do that now. The homework from last week was to try and solve the cargo ship problem on Mosul, which I think, I'm not sure whether everybody's done. Probably not. It's boring because the whole code is here. But the optimal solution was to, well, the income is 26, but I think we solved it before, so, and you take 3 times A, no B, and 2 times C. I think there were several optimal solutions, but the one that I got from Mosul with this code was this one. Second was a bit more challenging because you were asked to do telecoms, and what I got was subscribe to Lemon. Of course, if you don't remember what the telecoms example was, then this is not meaningful, but the answer is subscribe to Lemon and 4. And from Lemon, you should get 93 minutes and 0 paid minutes. And from 4, you should get 103 minutes and 310 paid minutes. And the total cost was £103.10 per month. I think you solved it. Was that hopefully what you got?
I think so. I've not got it.
310, I remember you had that. So
That's what I got.
yeah, okay. Good. So to those who actually do the homework, you can still put your marks down here. I've put 2 for the branch and bun because it's a lot of work, and then 1 each for you solve each of these. So we've been going through all the leftovers so far today, and there we continue. Because what we started looking at the end of not yesterday's, but last week's lecture was this project planning. And it's kind of a simple example, as I said last week as well, of how you would schedule projects that compete for resources. So in this case, we only have one type of resource, and every project has a certain requirement for that resource. But of course, you can generalize it quite easily to several different types of resources. And I've actually got some data. Okay, so what is the idea? The idea is that you have 3 projects to choose from in this simple example. It only becomes more interesting when you've got dozens of projects to choose from. Now, each of the projects has a certain duration of how long you work on it, so 3 months, 3 months, 4 months. And then the first project of that one unspecified resource needs 3 units of it in its first month, 4 units of it in its second month, and 2 units of it in its third month. And the second project needs 415, and the third project, which lasts 4 months, needs this much of the resource in its first month, second month, third month, last month. And we want to do these projects over the next half year. And how much of that resource we have available in each of the coming 6 months is given in this table. So whoever wrote it was very inconsistent because sometimes the month is T and sometimes the month is M, and it was me. But never mind. So last week we kind of started, and what we said was that we're going to have a decision variable which are going to be SPM, And this is going to be equal to 1 if project P starts in month M. Aha, so now I realize it was actually very smart to put different T and different M, because it's a different thing. We'll get to that. So I skipped the usual thing where the data. So here P is in the set of projects and M is in the set of months. And I'm being a bit sloppy. But that's okay. The full version is in the booklet. And if it doesn't start, then it's going to be 0. Okay? Otherwise. And that's all the decision variables that we need, really. So notice that the decision variable is not when the project starts. You don't have a decision variable that would be 1, 2, 3, 4, 5, or 6. But it's much easier to write it, or maybe even only possible to write it if you have a 0, 1 binary indicator variables for each of the months and each of the projects, which indicate that that project starts in that particular month. Okay. Yeah. Now, what are the constraints? I'll do the objective last. So the first thing we should make sure is that every project starts. Exactly once. We want to do them all, if possible. If it turns out that it's infeasible, we have to do something else. But in this case, we want them all to be done. It's just a matter of deciding when each of them should start. So how do we do that? The project starts exactly once. So that means that exactly one of SP1, SP2, SP3, SP4, SP5, and SP6 should be 1. And the other one should be 0. But that's not a linear constraint as it's written. It's a kind of a logical constraint. But the way to write this constraint as a logical constraint is that when you add them all together, not P, S, P, M, for all the months, I'm going to put 6. They should all add to 1. Okay? Now, how could 6 different 0, 1 variables add to 1? Well, they can only add to 1 if exactly one of them is 1 and the others are 0. So that does exactly what we want. Okay, there's something else other than 6. So maybe one doesn't want to put quite 6, because if the project takes 3 months, you don't want it to start later than in month 4, because if you started in month 5, you won't have enough time to finish it. So maybe instead of 6, you want to put 6 minus the duration of the project plus 1, which gives you exactly what you want. So if the duration of the project is 3, you get 6 minus 3 plus 1, which is 4. If you started in month 4, it runs in months 4, 5, and 6, so that's exactly what you want. And the one that runs for 4 months, you want it to start no later than in month 3, which you would get 6 minus 4 plus 1. And DP is the duration that was in the table, which I showed. So when you look at this, the duration is DP, the benefit will come to that, and the resource required is this, and the resource available is AM. So we've got this one constraint, set of constraints, because we want one like that for every project. What else do we need to make sure? We have to make sure that in every single month we're only running projects so that the total requirement of on that resource does not exceed how much we have available, right? So that's a bit of a tricky thing because, yeah. How do you do that? Okay, the constraint is it's kind of odd. So I'll write it anyway. So in month K, we have to look at all the months going from 1 to K. RP K plus 1 minus M times S E M. So this is what project P uses in month K. This whole thing. Does it make any sense? No. This is quite tough the first time you see it. So remember this R with P, so stands for the project. This is the age of the project. Okay? So when we had a table here, sorry for covering it again, but using T there. Okay, so RP1 is 3, RP2 is 4, and RP3 is 2. Now, when is the first project using this 3? Well, it depends on when it starts. If it starts in month 1, then it's using this 3 in month 1, and this 4 in month 2, and this 2 in month 3. But if it starts a month later, then it's using this in month 2, nothing in month 1, this in month 2, this in month 3, this in month 4, nothing afterwards. And if it starts in month 3, then it's using this much in month 3, this much in month 4, this much in month 5. Okay. So this formula here makes sure that we're actually looking at the right entry in that table of resource requirements. Okay, so if the project starts in month N, then this is going to be 1. And in, for example, let's say N is 3. The project starts in month 3. And in month 4, we're getting is 4 plus 1 is 5, minus 3 is 2. So we're looking at the second month in the project age, the project's duration. And then when k becomes, well, not much. You get the idea, okay? So this index here makes sure that I'm looking at the right resource requirement for that specific project. And I get many of them, but all of them are going to be, almost all of them are going to be times by 0 because I'm only starting in one specific month. And that's the one that's going to kick in. And all the ones are just going to be times 0, so they don't actually add. But we need to add this over all the projects. And we need to add one like this for every month. And this should not be more than the availability of the resource in that month. That's what the constraint is. I tried to explain it, maybe not very well, so you'll have to think about it in your own time later. And then we have these binary variables. Everything should be binary. So for all months and for all projects, we want this decision variable to be 0 or 1. And these are all the constraints. So if you were only interested in a feasible schedule of all the projects that never goes over the resource availability, then finding a feasible solution to this would be enough. But there's also an objective, and the objective is given by the benefit of each project. So there is something called the benefit of the project. And after the project is finished, we're getting this benefit from it. Okay, so if we start the project early, then like if we started in first month, then first one, then we get 3 times 10.2. If we started a month later, then we only get 2 times 10.2, and if we started even later, then we only get 1 times 10.2. And if we started in month 4, then we don't get anything for the project into the objective. Okay, so that again is a kind of a complicated formula. So we want to maximize the benefit. We have to add them over all the projects. Well, that's kind of straightforward. The benefit of the project is this much per month, and we just need to find out how many months the project is going to be finished. So we go from 1 to 6 minus the duration of the project, and this is the right formula, apparently. I knew why when I wrote it, so I have to reverse engineer. So for example, project 1. It takes 3 months. Okay, so if you start it in month 1, then you will have 1 to 3 months, and it's giving you some benefit. So if you look at your, this M is just my letter for 6. So if you started in month 1, this is going to be 1. The duration is going to be 3. So you get 6 minus 1 is 5, minus 3 is 2, plus 1 is 6. So you're getting exactly 3 months. And whereas if you started, say, in month 3, then it lasts until the end of month 5, and then you only get 1. And then this would be 3. So you get 3 minus 3 is 0, plus 1 is 1. You get exactly 1 month after the end of the project. Again, this is just a formula that tells you how many months after the end of that specific project until 6 months later. And then you times it either by 0 or 1. By 1 when you're starting in that month, and by 0 if you're not starting in that month. And that gives you the objective. Now I'm exhausted. And we've only finished the leftovers. Have you got any questions about this at all? Or is it just so strange and odd?
Is there a part of that where it stipulates that you've got to do all projects?
Yeah. Where? In the question or in the solution?
In the solution.
That is. You want to start it in some month. Exactly what? This is. So exactly one of the starting options has to be yes. Now, if you had a different question in which you were asking, in which you had a huge set of projects, and you would only be able to do some of them, and part of the model would be to choose which ones you want to do and which ones you don't want to do, then what you would put here is less than or equal to. Okay. So that would mean that you don't start the project more than once, but some projects you don't start at all. Anything else? Okay, so we don't quite have enough time to start the next thing, but I'll just do an emulate. It's a trailer for next week. So what we're going to be doing next week is looking at a different way of solving problems, so no more formulating again, but different one to branch and bound. And the one is based on the idea that when you have a problem like this, the linear programming feasible region is the whole gray area here. But your feasible solutions are just these points with integer coordinates. So there is a way to find out that you can, so if you could, for example, find a new constraint, which in this case is, I don't know what this is, I think that's x2 minus x1 is more equal to 1. No, it would be something like that. Yeah, something like this. Then you can cut off this area, and that's no longer part of the feasible region. But all your integer solutions still satisfy all the constraints that you have, including the one that you've added. And similarly, if you can find this one, which is easy, x1 is less than or equal to 2, then you've cut off this area here where there are no feasible solutions because there are no integer points. And now With these two constraints added, no matter what the objective is, you can easily solve the integer problem, because if you do the simplex method, what it's going to find is one of the corners as the optimal solution to just the LP relaxation. And all the corners now have integer coordinates, so you can easily solve the integer problem. But the whole thing, the whole theory is about how do you find these new constraints that you could add on top of the ones you started with, so that you wouldn't lose any integer points, but you would get rid of all the non-integer points. Next. Thank you.